go from here. From current slide. Okay. I thought I turned the projector on, but I guess you did. Okay. Now, let's do a little bit of quick review here. And this is what I started to say before I decided to wait until I got Screencast-O-Matic up so everybody can hear it. Okay. This, of course, one of my best classes ever. And how many research papers have been turned in now? One. Only one, okay? And guess what? We're running out of month, okay? We're almost halfway through this month, and the research papers are due before the end of the month. It'll be the last day of class, not the last day of finals. So please don't forget to get those done. I've returned, I think, to everybody the first lab and the first test. I'm still missing one, and only one, lab 2, so I need that in so I can return those. Everybody's done test 2, I've returned those. Lab 3, 2 people, that's the Moon Lab, have turned that in. I can take those anytime. Test 3, there's still 2 people missing on that. Lab 4, 2 people missing on that, and they're not always the same 2 people, by the way. Test 4, 1 person's missing that. Lab 5, more people are missing than have turned it in. Test 5, 2 people missing on that. Lab 6, maybe half of you have turned that in. And test 6, I think only, goodness, 2 people have, oh yeah, that's the take-home test. 2 people have turned that in, and here comes some more. Okay, so these will catch up quickly. All right, so that's where we are. Please, folks, don't let things get too far behind, okay? It's hard to catch up at the end, so try to get these things going now. Now, where are we now? We're in Chapter 20. Last time we finished Chapter 19. We did the lab for Chapter 19, and I gave you the take-home test for Chapter 19. We got started in Chapter 20. And we got most of the way through 20. So today, we'll continue in Chapter 20, and I feel pretty confident that we will finish Chapter 20 pretty quickly. Okay? When we finish 20, we don't do 21 because that wasn't in the little book that you got anyway. That's on geologic time. And we don't do Chapter 22, which is on the atmosphere. I wish we had time to do that, but generally we don't. Okay? So then we move into Chapter 23, which is weather and climate. So we'll probably just get into weather and climate today. We will have the lab, since I think we are going to finish 20 today, the lab that corresponds to 20. It's not directly all that closely related, but it is somewhat related. Most of these labs now cross over multiple chapters as we do them. So, the last 2 hours today will be spent in the lab that corresponds to Chapter 20. So that means from 1:30 to 3:30. Don't think it'll take you 2 hours to do, and I haven't decided yet whether we'll stay up here in this room or go down to the computer room, because there is a small computer component, but several of you have laptops or phones or other things you might be able to use. But if the rest of you do want to use that, we might go down to 256 like we did for the last computer lab. So we'll probably do that, but we'll see. Then on Thursday, we'll have the test for Chapter 20, the last 30 minutes. And my guess is that we'll probably not be ready for the lab. Well, we won't be ready for the lab for Chapter 23 because that's the visit to the Weather Center at Channel 13, if we can get it scheduled. And I'm hoping that we can get that done. We weren't able to do the planetarium lab, but hopefully we'll be able to do the Channel 13 lab. So, but we do need to finish the chapter first, so we'll do that, and then that day, that'll be almost the whole day. Maybe we'll get a little bit in, otherwise it depends on when they can take us there, but we will plan to have that on that day. Now, that being said, any questions from anything we've done so far? Okay, so today, finish chapter 20, start 23, have the lab for chapter 20. Thursday, continue in chapter 23, stop at the end, and have the test on chapter 20. And then next week, depending on how things go on Thursday, we'll talk about what day to try to schedule the lab, the trip to the Channel 13 Weather Center. Any questions? Okay. Just a little bit of review now. Chapter 20, there's Chris. Okay, chapter 20 has been shaping the Earth's surface. Chapter 19 was building the Earth's surface through the movement of the plates and volcanic activity and bending and folding and faulting of mountains and that kind of stuff. Chapter 20 is now the shaping, the grinding away, the wearing away of Earth's surface. Okay? In general, what feature of nature contributes to the most to erosion? It's involved with just about, not every bit, but just about every bit of erosion. What feature of the Earth's condition contributes to the most to erosion, or wearing away? Right. Second? Right. Okay. You're hitting the number one cause, and that's water erosion. But actually what causes the erosion is gravity, because gravity pulls everything downhill. So whether it's pulling the soil downhill, trees downhill, snow downhill, avalanches, landslides, mudslides, or whatever, and even pulling water downhill, gravity's doing it. Now, of the three features that contribute, gravity is doing the work of it, water is the number one. Water is the primary instigator of erosion. Okay? We talked about this some last time. When big old water droplets fall, the first thing they do is attach the soil, because they come down with a lot of energy, especially if they're coming from way up there. Okay? They have a large or fairly large mass and certainly a large velocity, and the combination of mass and velocity is kinetic energy, and that detaches the soil, and then the gravity pulls it away and runs it downhill. So, after water, the next major one, though not in every part of the Earth, obviously, is glaciers. And that's water also, and it's also gravity pulling it downhill, but now the water is in ice form. Okay? Now, as I said, certainly we don't have any glacial erosion around here, okay? Nowhere close, okay? But in significant parts of the globe, glaciers are your prime, or not prime, but a major source of erosion. So what are glaciers? Here's a decent definition. Masses of ice on land that move under their own weight. What moves them? Gravity. Weight. Gravity. Pulling them downhill. Okay? So that's what a glacier is. A mass of ice on land that is being pulled downhill due to gravity. Okay? Where did it come from? They form from snow accumulated over a number of years. Okay? Now, in our current situation here on Earth, just about every part of the globe is experiencing gradual warming. Okay? But that doesn't mean that still some areas are accumulating snow. You know, some areas are cold enough that it never gets warm enough to melt at all. So if it doesn't melt at all, it accumulates. And the more it accumulates, the heavier it gets. The heavier it gets, the more likely it is to go downhill. So these glaciers are formed from snow accumulated over a number of years. Some of these as few as 5 years. Okay, if it doesn't melt every year, which most places it is now, but some places not, then it builds up over years. Some of the glaciers currently existent on the planet have been building up snow from as much as 3,500 years, 35 centuries, 3.5 millennia. Okay, they've been building up snow, adding to the snowpack already on top. Now, there's two basic kinds of glaciers. Okay, the first of these is named alpine. Do you have any idea where that could have come from? The word alpine.
Alps?
Yeah, the Alps mountains in Europe. You know, a lot of this stuff was done first in Europe before it got even over here to the U.S. and we're just sort of Eurocentric, and they call them alpine glaciers. Actually, a better name for them would be this: valley glaciers. Yeah, all the ones in the Alps are valley glaciers, but why call them alpine when they could be in the Pyrenees, they could be in the Andes, they could be in the Rockies, they could be in the Himalayas? Why call them alpine? They're all valley glaciers, or a lot of them are. They form at very high elevations where mountains are tall, and where mountains are tall, typically the air is thinner, and where the air is thinner, it generally is a bit colder, and therefore they accumulate, these glaciers. Masses of ice accumulating way high in the mountains, form at the high elevations. They go down through the valleys. That's the lowest point, okay? And generally, things travel the path of least resistance, a lot like students, right? So they go down the valleys. So therefore, the better name for them would be the valley glaciers. But they're not the only kind of glaciers. There are others in areas that, not just way up high in the mountain, but just very far north, where you get very cold temperatures and snowfall. You don't have to be in the mountains. It could be in a plain, you know, any large area, and these are called the continental glaciers. They cover large areas of a continent, usually the far north and far southern continents. The major ones today are in Greenland in the north and Antarctica in the south. But there are continental glaciers other places. There is, I'm pretty sure this would be classified as one, in, I believe it's British Columbia, it may be Alberta, Canada, one of the two. Pretty far north, up past Jasper, Canada, is the Columbia ice fields. That is a continental glacier. Big, sprawling, flat area, and the glacier is moving down. Now, the sad news is it's melting faster than it's moving. Okay? My wife's family, we took a trip up to Alberta and then British Columbia, Canada, one summer, and we went to see the Columbia ice fields. And back when they were discovered, at least by European-type people, of course, the natives have known about them for probably centuries, but I'm guessing it was around the 1800s or so. I don't remember exact date. And at that time, someone happened to drive a stake into the ground right at what they call the tongue, I believe it is, of the glacier. Right at the very end of the glacier where the last of the ice was, right where it was melting. Okay? And since then, the glacier has been retreating. Now, it's coming downhill. Yes, that's what it does. Gravity's pulling it down, but it's melting faster than it's coming, so the actual end of it is now more than a mile up the way. You don't even see the end from where that stake was. You have to walk about a mile, and and then you start seeing the glacier. Okay? That shows how our atmosphere has been warming. Okay? So they're not only in Greenland and Antarctica, but that's where the major ones are. And even those typically are shrinking. Okay? They're melting. They're getting added to because it snows more every year and it doesn't ever warm up enough to melt completely, but they still are losing ground just about everywhere. Occasionally you'll hear Antarctica has a really cold year and it will actually they'll grow again, or Greenland, but in general they're retreating. Now, going back to alpine glaciers or valley glaciers, there is a beautiful park, lots of beautiful parks in the U.S., and I think I've already said this about Yellowstone. By all means, sometime during your adult life, try to get to Yellowstone. I mean, it's the #1 first national park created. It is an incredible, incredible, incredible place. Try to get there sometime. There are many other great national parks across the U.S. One of these, my wife and I went to one summer, and it's called Glacier National Park. It's up in Montana. A little bit of it maybe in Idaho, but mostly in Montana. And it actually spills over into Canada, but that's the Canadian National Park there, not ours. Okay? The sad news is, back when it was formed, made a national park, I don't remember how many, it seems like there may have been 16 or 17 fairly major glaciers in Glacier National Park. And you can see many of them. Now I don't believe there's more than 5 or 6, okay, or just fragments of what they used to be. And there is some thought that in the not too distant future, there may be no glaciers in Glacier National Park, which will be really sad. Any of you ever heard of Ernest Hemingway? Very famous writer. Lived and wrote mostly in the World War I and between World War I and World War II type time frame. That's the 19-teens, 20s, into the 30s maybe. I don't know, he may have even still been around in the 40s. Okay? One of his fairly well-known novels, and he has bunches of very well-known novels, but one of his was The Snows of Kilimanjaro. Anyone know where Kilimanjaro is? It's one of the tallest mountains in the world, not nearly as high as elevation as the Himalayas, but above the prevailing countryside is one of the tallest mountains in the world. The Himalayas are way up on a ridge, so Mount Everest is the highest elevation, but where it sticks above the prevailing area is not as tall as it is Kilimanjaro. Now, the funny thing about Kilimanjaro is it's very close to the equator, okay? And but being such a tall mountain, it used to have glaciers on it. And Hemingway wrote this, I think, back in the 30s or 40s, and it was The Snows of Kilimanjaro. You go to Kilimanjaro today, you'll hardly see any snow at all. I mean, you're standing down looking up at the mountain, there's hardly any snow to be seen. In the coldest, which isn't very cold, and most humid part of the year, yes, snow will fall up there. But then in the drier part and a little bit warmer part, it all melts away. So the glaciers that used to be in Kilimanjaro, not there anymore. Okay? It's a pretty sad situation for our globe. We are warming. Okay. So that would have been, again, a valley glacier, not a continental glacier. Okay. What do you think this one is? Valley or continental? Where is the glacier here? This snow on the side of the mountain, that's not glacial snow. This is the glacier. All right? Where is it? In the valleys. This is a valley glacier. It's way up high in the mountains. And that glacier is not just, it is frozen water, the ice, but it's not just sitting there. Ever so slowly, it's creeping down the valley. Way slower than my hand is moving now. You don't detect any motion at all, but it's always moving downhill because of gravity. Very incredibly slow. Now, if you picture this valley here, it goes really deep, really deep. But here's the glacier top here. So that glacier is filling enormous amounts of that valley. In fact, most of the valley. And if you think about how deep that must be, think of the weight that is on the bottom of that glacier. It's enormous, enormous amount of weight. Okay? That leads to what we're going to do next. We're talking about glacial erosion. Now, again, it's not something we worry with here in Alabama, ever, okay? But there are three mechanisms by which a glacier will erode soil, rock, and everything else. First, let's go back here. If this picture extended far enough downhill, down here, and we could see far enough here, at some point is the beginning of the glacier. Okay? And the glacier, from that point on, is melting and stuff, but that is the front part of the glacier. As it's moving downhill, it's acting like a bulldozer. So that's what the first thing they say is bulldozing. Okay? All the glaciers are pushing ahead of it any rocks, any boulders, any soil, anything that's in its way is pushing it ahead just like a bulldozer does. Okay? Now, get my globe. There have been at least 4 of these very, very, very major events that have happened over the long, long, long course of history, called the Ice Ages. Okay, they have movies about them, right? Okay. Now, in the Ice Ages, okay, here's Greenland here, there's Antarctica down here, okay? This is where most of the continental glaciers are, but Canada has some. I'm sure Alaska has some. They also have valley glaciers. But the flat part of Canada has these continental glaciers. But back during the Ice Age, the glaciers came way, way south. I don't think they ever reached Alabama. I don't know. I doubt it. But they came way down into the Midwest. And as they came, now these are the continental glaciers, that bulldozing and these other 2 events here, those glaciers were moving downhill. As they came, they were scraping along the soil in Canada, okay? And carrying with that, with them, the soil at the bottom of it, okay? And then when they finally started retreating, they started melting and dropping off that soil. And that's why our Midwest, Nebraska, Iowa, Indiana, the Dakotas, all that area there, thank you, Canada. Canada contributed feet after feet after feet of topsoil because those glaciers brought it down, melted, dropped it off, and went back north. Okay? That's why our Midwest is some of the greatest, most incredible farmland in the whole world. Literally. Because it all got scrubbed off of Canada and headed south. Okay, bulldozing was part of that. Okay? That's the front part of the glacier. And those areas, when they were pushing along these rocks and boulders and soil and everything else in front of the glacier, And finally, the glaciers quit moving, and this happens really major in the valley glaciers, okay? And when it quit moving and started retreating, well, it left all those rocks. It doesn't take them back with them because it's melting now, okay? They're dropped off there. What they did, they formed natural dams, okay? And some of those are called moraines. And we were up in, I believe it was in Canada. It was one of the most beautiful lakes we saw, was named Moraine Lake. You drove up to it and you just saw in front of you great big old boulders, the size of multi-story buildings, just sort of randomly lying around up there. That's where the glaciers had pushed them to right before they started retreating. And when they retreated, they melted. They formed a dam there, and then the melting water filled the lake behind the dam. So that was called Moraine Lake. Now, always remember that name because of Moraine Lake. Beautiful, beautiful lake. That's not the only thing it's doing. Pushing ahead of it, the boulders and everything else, it's also grinding as it goes. If you think of the bottom of that glacier is grinding along that valley or that continent, wherever it is, grinding as it goes, okay? Carrying with it rocks and things. Now, these two things do go together here. The plucking, and I don't know if you're familiar with the activity of water and ice. When you add pressure to ice, it tends to melt. But then when the pressure releases, it freezes again. Have any of you ever done any ice skating? I've tried, and I am miserable at it, okay? My ankles just will not cooperate. But that's how ice skaters do. They're on that very thin little blade, that's a lot of pressure. It melts the ice just in front of them as they go over, and they glide along, and then it refreezes right behind them, okay? Now, on those rare occasions, and one happened, about 4 or 5 years ago, the snowcopolis, or something like that, they called it on the television, when suddenly, I think it was maybe March, maybe a little earlier than that, they had called for maybe a dusting of snow this day, okay? But what happened, we almost got a blizzard, okay? Not quite, but it was pretty close. But the thing that was even worse, we were way, way, way cold that night before. And the ground was below freezing, okay? And then the snow came. Now, that's the thing about here in the southeast, most of the time we don't get snow when it's that cold. We actually used to say, oh no, it's too cold to snow. Because down here, you almost have to be a little bit warmer for the snow, to have drop out of the air. And then it melts and, you don't really get to play in it very well. But this day, it was cold. And the snow came, and it didn't melt. And the snow fell all over everything. And I don't know if you've ever driven in snow like that, but what happens, your car wheel, if you're the first to drive over there, it packs the snow, grips the snow, you roll on by. But once you roll by, then that snow that was puffy like this has been pressed down, melted, and then your car wheel releases it, the pressure is released, and now it refreezes as sheet ice, okay? And after very few cars go over it, but the more cars that go over it, the more that happens. So after a while now you have ice skating groups, okay? You don't roll over it anymore, your tires spin like crazy. And that's what happened that day. The first few people to get out of town got out okay, but they left grooves. And the next people went along after them in the grooves, and after a while, nobody was going anywhere. I happened to have had a doctor's appointment that day, that's why I remember it so well, at Kirkland Clinic. And it was a Tuesday, because that's the only day the hematologist sees patients. And it was a while I was in there, the snows came, and when I went to leave, I couldn't get out because no one could get out the parking deck, because no one could get on the roads, because everybody was sliding on the roads. So I was stuck at Kirkland Clinic. My wife said, I called her, she said, yeah, go and try to get something to eat for lunch. I tried to call the school, I couldn't get an answer here because they closed classes. No one knew this was coming. They had canceled classes for the rest of the day, so I couldn't get anyone on the phone. So I ate lunch, and then I was able to get out. And I got to the last hill before I got home. I only lived about 3 or 4 miles from UAB. So that last hill, I just couldn't make it up. I slid around, so basically just like kind of backed in and slid back down the road and parked next to the curb and stopped. And then I got out of the car and was walking, got within sight of the house up that hill, and my phone rang. Answered it. My wife said, "Can you come get us? We can't get out." Okay? So I went back to the truck, got in the truck, and I couldn't go up the hill, so I had to back down the hill. I hoped nobody was going to come around that bend at the bottom, because I couldn't have done anything if they had, and they didn't. And I managed to pull it back into the driveway and then turn and get on. And I met them at a given corner, and then we went back. And she didn't want to go back the way I did, so we tried a different way. Now we got 2 hills from the house, we couldn't get through the thing. So we got there, couldn't get any further. People were sliding into everything. We asked this one, the nice old houses set way back off the road, and a guy had just driven home, and we went and said, "Look, can we park our car in your driveway because we're scared to leave it on the road here?" He said, "Absolutely. My wife's already there. She's not going anywhere till this melts. Feel free, park anywhere you want to." So we pulled into the driveway, and we walked the next 2 hills and got home. Got home just in time. We were beginning to thaw out, warm up a little bit, and one of Karen's workers called and said she had left like 2 hours earlier, trying to get home to get her kids out of daycare and get them home. She had left at least 2 hours before, and she said, "I did not get to the next exit on the expressway. We were just at a standstill. When I finally got there, I got off the expressway. I'm going back to the office. I'm going to spend the night there." And Karen said, "Don't do that. Come on to our place, because we live pretty close." So she told her where she thought she could get as far. So she said, "Go meet Emily." So left the house again, up those hills, and finally met Emily coming up the 3rd hill. She couldn't even make it to the 2nd hill. So I met her there. We came home. We had a good time after that. It was incredible. The more people that went, the slicker it got. Well, all that weight, all that pressure on these rocks and everything else that's at the bottom, that pressure melts the ice, and then it refreezes, basically with those rocks as giant pieces of sandpaper, okay? Only they're boulder paper, and they, going downhill, grate and grind and produces this powdery, silt-sized rock flour. Remember back when I said there are 3 classes of soils by size. Sands, which are basically up to 2 dimes in thickness. Okay, yeah, I've got 2 dimes. The biggest sand particle would be the thickness of 2 dimes together, and then they go down to just a fraction of a dime. And then the very smallest ones, which would be 2 1,000ths of a dime, slice that dime into 1,000 equal pieces. 2 of those put together would be the largest piece of the clay particle. And then the things in between are called silt. And most of the silt comes from grinding sand particles, and that basically, and in the Midwest, they have a lot more silt than we do because they had the glaciers grinding those sand particles to bits. And then the third, which I've already mentioned, is the plucking. The glacier water freezes, picking up surrounding rock, and now you've got just a terribly rough, brittle, abrasive surface at the bottom, and that grinds along, producing the abrasion. So these are the 3 mechanisms whereby glacier erodes the soil, pushing the soil ahead of it as a bulldozer, abrading the soil like crazy, making this fine silt-sized flour, which makes that great topsoil in the Midwest, and then plucking up rocks and other things, freezing them in place and pulling them along, grinding as they go. So those are the three mechanisms of glacial erosion. Now, what's the effect of this? Before the glaciers, okay, this is, remember when we talked about our landscapes? And we talked about the very young landscape when everything was deep valleys, very sharp V-shaped valleys. And then when it got a little more mature, you got sort of rounded action and the valleys started filling in and stuff like that. This is sort of beginning to be a mature landscape, but then here came the glaciers. And the glaciers filled the valleys. And as they fill the valleys, they bulldoze, they abrade, and they pluck, and they dig out the valleys as they move, because they're moving very slowly, but with all that enormous amount of weight on top, and all that plucking and frozen stuff in the bottom, grinding their way along. And what they'll do is then dig out, and those glaciers we saw earlier are in the process of digging out those valleys, making them rounded rather than sort of V-shaped, okay? And you'll have places where one glacier will stop, and that's called the hanging valley. You'll have places up here high where the glaciers are worn down, and now you have a rounded type mountain here, but the glacier wears it down, making it sharp and deep. And that may form a horn here. And arete would be the ridges that you have between the glaciers, whereas here it was sort of smooth, now it's pretty rigid. You have rock basin lakes where the glaciers may have stopped and melted and retreated and stuff, bulldozed down and stuff. So you have a series of lakes like this in various locations. This, I think, is called a cirque, I think is how you pronounce that. And that's a hollow type area that the glacier ate out a little bit and then left a lake in its place. More rock basin lakes here. The hanging valleys are where one glaciers stop and intersected with the second one that went deeper. That makes a hanging valley and also makes beautiful waterfalls, by the way. And then you have the U-shaped valleys as opposed to the V-shaped valleys before. So this is ways that the glaciers erode the existing landscape. Okay? Any questions? All right. The third of the major contributors to erosion is wind. Now, wind is the one that is not predominantly caused by gravity. Okay? Gravity has very little to do with the wind. I won't say nothing, but very little. Lots to do with water, lots to do with, remember the two types of land movement? Remember what they were? The real slow one was called soil creep, and when it's faster, it's called landslides. Okay? Both of those caused by gravity. That's the land being pulled downhill. Water being pulled downhill, that's the second. Ice being pulled downhill, that's glacier erosion. Wind erosion doesn't have much to do with gravity at all. And similarly, it's considerably less efficient than either water or ice, or certainly soil itself. Okay? Because the wind doesn't have the mass. Remember, to get the kinetic energy, you need mass and velocity. You have the velocity sometimes, but not the mass. So it's considerably less efficient than water or ice. Two major processes, and these are not too far from what we saw with water. Okay? A little bit. The first is called abrasion. Okay? Now we saw that same term back here with the ice, abrasion. Scrubbing along, tearing up, grinding down the soil. Well, now we're doing it with wind. This is, they call it natural sandblasting. Have you ever operated a sandblasting machine or seen them being operated? Basically, it's pitching very high volumes of air and velocities of air with sand particles in them against the surface to try to wear off the corroded, moldy, mildewy type things. They do this in buildings downtown and places like that. Facelift, okay? Not a great thing to do, I don't think, because you're wearing off the surface, okay? Every time you sandblast, you're taking more of the original surface. After a while, you don't have the rock there anymore. Okay, well, the wind does this naturally sandblasting. It picks up little sand particles or little gravel particles or other things and blows them against rock, and that's your natural sandblasting. Now, this produces what they call ventifact. Venti means wind. So these are the artifacts left over from wind. And some of these are very, very characteristic of wind. Okay? For instance, I don't know if you've noticed it or not, but most, not all, most of our winds are what we call the prevailing westerlies. You go out just about any time and notice where the wind's coming from. The odds are kind of somewhat from the west. Maybe northwest, maybe southwest, but generally from the west. Every now and then you'll get a storm coming from the east or from the south, and occasionally from due north, but the prevalent is from the west. If you picture, did y'all watch back in April, was it 2011, when they had that huge line of tornadoes that came through? Did you watch that on television? Anytime you have weather systems like that, you'll see them come in from the west and move to the east. That's the prevailing thing. Why? The spin of the earth basically is what's causing it in a roundabout way. So you usually do have prevailing winds. And if they are coming from one direction, then they're tending to wear off, because of this abrasion and stuff, the wind carrying sand particles or other particles with it, breaking down rock over time. It takes a long time for this to happen, but you'll usually find the faces of the rock to be slanted in that direction with prevailing winds. Now, if you ever have a major change, then you can have some prevailing winds doing that. But most of the time, the prevailing winds don't change that much. Okay? And this would be what they call the ventifact, the characteristic shaping of the rock due to prevailing winds. Now, it's not just rock. When I was in California in the Navy, that road that went from San Francisco up to Sacramento, the capital in Sacramento, there was an interstate. Every tree in it was like this, because prevailing westerly winds just blow in off the Pacific, blow hard, and those trees were all leaning toward the east because they just couldn't stand that wind. Okay? So, those trees were ventifacts. They were the result of the artifacts of the wind. The shape can depend on the prevailing winds, and that's what we're just talking about. So there's one, abrasion, that's breaking off the particles that are on the surface. The second of these is deflation. That's when that loose material that's been broken off is picked up and carried off. So it's a lot like what we talked about with water. You first have detachment, and then you have transport. You first have abrasion, that's your detachment, then your deflation when the wind carries it away. So that's when the loose material is picked up by the wind, carried away, and then it's used for sandblasting the next rock. Okay? So it's an ongoing process there. Now, what's the result of this? You have these wind-blown deposits. Now, they have the special name, especially if they're near the beach, but they don't have to be near the beach. They're called dunes. Okay? But you see these all the time at the beach, where the wind has picked up when it's very, very stormy, like hurricanes and that kind of stuff, picked up the sand particles and then dropped them off, and then it doesn't blow as hard anymore, so you have these mounds or dunes of sand just inland. Okay? Similar to that, but not forming dunes, is just a broad expanse of wind-blown soil is called loess. It looks like loss or something like that. It's pronounced loess. This is fine dust that is deposited over a very large area, not in dunes or ridges or things like this, but actually in broad areas. Does anyone remember historically what happened back in the, I think it was around the 1930s or so? Major event, especially out in the Midwest.
It was a big like big sandstorm.
Yes, you got it. The huge windstorms we had there. It was actually called the Dust Bowl. Okay, that wasn't a football game. It was what happened. And boy, were we ever kind of dumb. When we were first settling the U.S., we just happened to have lucked into being a time when it was fairly high rainfall for that area. And we were moving west, and boy, those prairies were fantastic. They were flat, not many trees on them. Well, that wasn't good for building houses, but you know, they lived with that. And thick, deep, rich topsoil, and pretty decent rainfall. So they went in there, and our prairies, they call them the Great Prairies, you know, they're incredibly amazing. The grasses that had grown there, because remember these are the really rich topsoil brought down from Canada, thick topsoil. The grasses grew, the roots went way down in them, because it typically was sort of a dry environment, so the roots went way down looking for moisture, and the roots held the soil together. It was just a great system. Ecology usually is, you know. It found the best way to grow things. So we came in, meaning settlers, mostly European settlers, came in and said, man, look at this great farmland. It's level, it's flat, it's get decent rainfall. Let's plow up this thick, heavy, mean, nasty-looking grass and plant us some corn and soybeans and row crops and wheat and whatever else. And for several decades, I mean, they harvested some good stuff. But then the real weather patterns, the normal climate, which was much drier, came in. And with the drought, the crops quit growing. And without those root systems of the prairie grasses, nothing was there to protect the soil. They had removed all the ground cover, removed the grasses, removed the roots that held them in place, and now there was nothing. And the winds came whipping down the plains, prevailing westerlies, and they blew the Dust Bowl, the sandstorms up. There were times you could not see because there's so much soil being blown. Some of that soil landed in Philadelphia and other places on the U.S. eastern coast. It was incredible. We really, literally raped the soil. You know, the wind, dry conditions, which was actually the more prevalent climatic conditions that the plains were used to having. We just happened to have gotten there at a time when it was wetter than normal. And we really did a bad job there. Well, those deposits that came over large areas, that was loess. And that quite often is that silt-sized, powdery, floury type sand particles that were deposited there. That's why the Dust Bowl was so bad, because they were very small particle sizes and just blew all over the place. If you find that loess, it's usually really, really good soil, but it's also not well articulated, you might say, to hold in place well. Okay, so that's your wind erosion. Now let's go back to development of those landscapes. If you remember back, I'm just going to fly through some slides here. Well, I went too far, too fast. Well, maybe I'm wrong. Yeah, there it is. The stream bed evolves over time, and you had the youth, the stream, youth, maturity, and old age. Okay? Now, screen forward, and we're going to talk about development of landscapes. And look at what we use. Okay, we'll get to it in the next slide. We use the same terminology. So what are these landforms? What do we mean by that? Landscapes are big areas of land. Landforms are the surface features. Okay? If you were to talk about the landforms around here, I would say Red Mountain would be a landform, Shades Mountain, the things that characterize. I don't know what caused it, but when you're on the the Western Superhighway here, and you go just a few miles toward Birmingham, you crest the hill and you see the whole city of Birmingham out there. You're somewhere way up there, and that's a landform. Okay. If you go to Interstate 22, Summerton, Alabama, sits way up high on the thing. You can see for miles. That's a landform. Okay. These landforms are the Earth's surface features. Some of these are very broad features, like the mountains. Red Mountain, Shades Mountain, Double Oak Mountain. Those are the mountains, broad features. Also things like plains and plateaus. And I'll just give you a small example of that. Y'all know basically where Columbus, Georgia is, and Opelika, Alabama, and that area right close there. What's the city called? It's right across from another city. Right across from Columbus. You go a little bit further north, I think, from Columbus, and you reach this place called the Plateau. It's called the Fort Valley Plateau. And it extends over into Alabama too. Some of the best peanut growing area in the world. Elba, Alabama is in that. That plateau is just fantastic for growing peanuts. The plains I mentioned out west, the plain type areas. Those are the broad features. Then we have the minor features. These would be the hills, the valleys, the canyons, and that kind of stuff. And this would be like Shades Valley, the hills. Isn't Vestavia basically built on like 7 hills or something like that? These are the minor features, okay? And then the general areas of these are based on either the rock structure, weathering and erosion, or what stages of erosion have occurred. Now, these would be some minor features. This is our farm in Georgia, small farm in Georgia, okay? My younger brother my sister lives on the southernmost part of the farm, okay? She's up on a clay hill, and, it's hard digging anywhere. Down in the valley, she's surrounded on either side by swamps, so her mosquitoes are terrible, okay? Low areas there, and that came from some of the preventers. I won't call it rock structure, but it's pretty close to it. The soil under that was what they call a Selma chalk. Selma as in Selma, Alabama. That's where they have it here. And that chalky type stuff, when the acid rain hits it, it dissolves it, and the land sort of sinks. And that's what gave her the swamp on this side and the swamp on that side. But she's up on the clay hill. Then across the road from her is where my younger brother lives. Sandy, sandy, sandy. She's up on a clay hill. Everywhere in his yard pretty much is sandy. Okay? Then you get over to our part of the farm, and we're up on a hill again, and that is some of the hardest, meanest, most ornery clay I've ever run into my life. It's so hard. When they were digging out the foundations of our house, the guy on the bulldozer was beating himself to death. He could not get the bulldozer to crack through that hard clay. It was almost like rock, okay? Then you get down to the far northern part of the farm where my older brother lives, and sand again. I mean, just such deep sand that's just incredible, okay? So those would be the minor features. Clay hills surrounded by sand. Well, the sand is washed off the clays into the valleys, and that's what produces it. The sand is collected in the valleys. So what were the generalizations based on? We'll say here, the rock structure, okay? Most of the underlying ground, rock here is limestone, and that's why you have sinkholes, okay? You have other features like this because the limestone will erode away because of the weathering, chemical weathering. So the underlying rock structure. But you have other places like Stone Mountain in Georgia, just a huge chunk of granite, okay? It's not going to wear away at all, or very, 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 very slowly. So the generalizations are based on what's the underlying rock structure, okay? Then what has your weathering and erosion been like? Everywhere in the southeast, erosion is major. Okay, Kayla is here. All right. We're now short just two people, Lauren and Jacory, the two last part of the alphabet. Okay. So what has the weathering been like? Everywhere in the southeast, the weathering has been intense. Why? If you think about the two major features of weathering, I don't know if we mentioned this earlier, but I'll say it now. Water and temperature. Okay? We have great rainfall. Thank you, Gulf of Mexico. If it weren't for the Gulf of Mexico, we'd probably be a desert. Okay? Because we're so far from the Pacific, the rains would all peter out before they got to us. But we have the Gulf of Mexico that keeps pumping water up. We have a fantastic water supply from the Gulf of Mexico. However, that high quantities of water is a big contributor to erosion, weathering and erosion. And number two is temperature. Down here in the south, we're subtropical. We'll talk about this in a later chapter. And the higher the temperature, the more the chemical weathering you have going on, the more the biological weathering you have going on. So we got it both. So our soils are some of the oldest, most depleted soils out there. Number one, because we farmed them to death, but number two, because they've just been exposed to these high temperatures and high flushes of water, washing the nutrients out. So the weathering and erosion has been major here. The stages of erosion, that means how far along is it? And unfortunately, ours is pretty far along. We talked about in the Midwest, the topsoil is measured at feet. Here, our topsoil is measured in inches, okay? We usually don't have much topsoil at all because we've weathered away and eroded away for decades, centuries, okay? Now, let's look at each of these individually. First, the rock structure determines the shape of the minor landforms. That's what makes Red Mountain shaped like it is. That's what makes Shades Mountain shaped like it is. That's what, whatever the underlying rock is, that pretty much determines the shape of the minor landforms. Now, what contributes to that? Well, what type of rock are we talking about? Now, it's hard to say hardest and, whatever. Igneous rock is usually pretty hard. It's pretty erosion resistant, but nothing ever can resist erosion completely. The igneous rock is usually pretty good about avoiding erosion, at least for a while. Metamorphic is the most resistant to chemical weathering. Igneous, pretty resistant to physical weathering. Metamorphic, very resistant to chemical weathering because its crystal structures would change so much. But sedimentary rock, which limestone is, and sandstone, all these very susceptible not only to chemical weathering but also to physical weathering. I mean, way bad. Okay? And unfortunately, that's what we've got lots of. Sedimentary rock, either chemical sedimentary rock, like limestone, and classic sedimentary rock, like sandstone. You go up to Winston County or many of those counties up there, and sandstone's all over the place. Aniana, they mine sandstone up there for flagstones and other things like that. And then some of these rocks just have a real bad attitude. No, that's not what we're talking about. The attitude of the rock means how is it facing? What is, what is the orientation of that rock? Okay, it's the effect of disturbance by the faulting or folding. If it's been pushed up, and faulted. I mean this seriously. When you drive up 65, a lot of 65 has been cut through hills and maybe portions of mountain. Take a look at the side of the road. Notice, is it flat? Okay. Are the layers fairly flat? In some places like 22 I was talking about that goes to Memphis, a lot of that layering is flat. But 65, some of those rocks are like this. And you think, what has caused that? That was caused by the faulting or folding of those rocks millennia ago. Okay? That's the attitude of the rock. How is it facing? How has it been disturbed? How has it been changed? Faulting and folding can hasten erosion. In fact, most of the time does. Because now, rather than flat plains, you have plains like this, and water just naturally runs down that. Grit runs down it. It just, it hastens the erosion process. So that's the rock structure. Okay? Weathering and erosion processes, this was the second one. We did some talk about that. Influenced by and controlled by such factors as climate and elevation. The two main parts of climate, temperature, moisture. Okay, what I was talking about before. Secondly, elevation. How high is it? And how does that affect what's going on? The higher the elevation, the more exposed you are to that prevalent wind and that type of stuff. Down in the valley, you're a little bit safer. I mentioned the clay hill we're on the farm. I lived on that farm my whole life, from the time I was 4 years old until basically I left the farm, probably to get married at age 35. So, it was a long time I was living there. I never knew how much wind was on that hillside because no one lived on the hillside. It was just a pasture, we were just over there. Never noticed. Boy, we built our house there. We can't keep wind chimes up. We can't keep, it blows everything. We got home last time, between the breaks between spring and summer. Our little tool shed, tool thing that we had at the end of the house, blown away from the house, twisted around upside down. And it was packed with stuff. It was heavy, and it was just completely torn up, okay, ripped, so we had to move things around, thinking of building something a bit more stable. Because, influenced by, elevation. We're up on a hill, nothing to stop the wind, it blows. Okay, as I said, the temperature and the moisture. When those are your prevalent things, warm, moist climates, chemical weathering dominates. And here's the general rule of thumb they use for this, especially temperature. I'm going to give it to you in Fahrenheit. You can transfer this to Celsius if you wanted to. But for every 10 degrees above 40 degrees Fahrenheit, 40 degrees Fahrenheit is probably not even our average low in the worst part of winter time, okay? When you have a 40-degree day, you talk about how cold it is. Now, certainly it gets much colder at night, but in the daytime, most days get about 40. For every 10 degrees you're above 40 degrees Fahrenheit, you double the rate of chemical weathering. So when you go to 50 degrees, it's double what it was at 40. When you go to 60 degrees, it's double what it was at 50. When you go to 70, and guess what? It's now 90 degrees out there. With lots of moisture, chemical weathering is happening so fast, it's unbelievable. Okay? So chemical weathering dominates when you have warm, moist climates. Landforms are usually softer, rounded outlines. The Appalachian Mountains, rounded. You don't see many jagged peaks in the Appalachians or anywhere here in the southeast. Now, what if you're in the drier climates, like go further west? Now mechanical weathering dominates. If it's dry, usually the sand is loose, the wind blows, and that abrades the sandblasting. Here you have sharper, angular outlines are much more common than the rounded outlines you see in warm, moist environments. So that's how weathering and erosion contribute to the landforms. Now this is where I meant to. Notice the stages of development of landforms. This is the one I was saying is just like the stream development. Youthful, maturity, old age. And there's the, well, it didn't show it, did it? Yeah, those are the figures. Okay, let's now do the landforms. All right, stages of development, youthful, maturity, and old age. Here we are all over again. These describe the cumulative effects of the formative processes of now your landforms. Before we were talking about stream beds. Now we're talking about landforms. Hey, almost the same thing. In the youthful, the weathering and erosion effects are just in the beginning stages. You'll see a lot of angles. You'll have steep peaks, narrow steep valleys, V-shaped valleys. That's your youthful landscape. Once they've worn away, either chemical or physical weathering, mechanical weathering, now the peaks and the areas are a little more rounded. The original structure is worn down, rounded peaks, slopes are a little more gradual. Some of the soil from the top is worn down, filled in the valley, so the slopes aren't as great as they were before. And then in the old age, okay, characterized by nearly flat, rolling plains. And here are a couple of these weird little terms they throw in here. The peneplains, nearly flat surfaces, whereas the monadnocks are hills of that resistant rock. And I would say, or resistant clay. Clay is pretty resistant itself much of the time. Now, when I read this, I think of Auburn, Alabama, okay? You know, they call it the plains, okay? Everything, in fact, the coastal plain, anything below Montgomery pretty much is fairly flat. You do have areas where you have more resistant rock that stick up there. These would be the monadnocks. What a weird name. It's a pretty word, too. Now, rejuvenation. Everything that's worn away, eroded away, things move downhill. Later, it's uplifted, and you build new soil, new hills, new valleys, new whatever. It's all a cycle. Remember the rock cycle? This is the cycle too. Next chapter, we'll talk about the water cycle. Every situation has these cycles in it. So after things have been worn down, old age, soil has been eroded, made its way down to the Gulf of Mexico, the pressures there are going to build, and somewhere land is uplifted, erosion begins again. All right, that's pretty much the end of this chapter. How are we doing on time? Oh my goodness, almost 1:30, isn't it? Could we have timed it any better? That was all luck, okay? Let me hit a few features here. In your text, not on the slide set, is a valley glacier in Mount Logan, Yukon Territory. I believe that's in Alaska. If it's not, it's in Canada. I don't know which Yukon we're talking about here. It's a valley glacier. You hardly see the valley. It's filled up the entire valley, okay? Very nice picture. Unchanging as the hills is an old saying. They're always changing. The change is just really slow, but they're always changing. Science and society, we talked about it several times. Acid rain, Okay? I said moisture is what controls chemical weathering. You add a little bit of acid in there, and boy, the weathering picks up big time. That's a great little blurb on page 518 to read, and you see some of the pHs that you talk about. Hydrochloric acid is one of the strongest acids anywhere. Would you have any in your body? Your stomach. Your stomach has some of the meanest acids in the world in it. That's what breaks down your food, you know. Fortunately, your stomach lining is a marvelous set of tissues that resist acid erosion, you might say. But what if you do get erosion there? Ulcers. And that's why ulcers are so incredibly painful, because that acid is so strong. Mostly hydrochloric. And hydrochloric is even stronger. Your gastric or stomach acids, they're just a little bit less acidic than hydrochloric. And then lemon juice, I used to like to eat on lemons, you know, not doing a good job on your teeth. Okay, that is eating away your enamel. Vinegar is next. Carbonated soft drinks, unbelievable, they're that acidic. Whoops, what are you drinking? No, coffee, that's almost as bad, not quite, okay. Then grapefruit, really acidic. Oranges, not quite as bad, but so then you get acid rain. Tomatoes, potatoes, natural rainwater is still slightly acid. Milk is only moderately acid, just slightly. Pure water is right at 7. So, well worth a read. The person behind the science in this chapter is John Wesley Powell, who was obviously a character and a half, and he did a lot of work in describing landscapes and things like that. Well worth a read there. Good paper topic, however, this cannot be your source. You have to get your source outside the book. Okay? And then another picture of a melting glacier, a valley glacier. They don't say where this one is. And then you see the stream flowing downhill from that. I say it again, I say it every chapter, nothing replaces reading the chapter. Okay? This chapter has a notoriously short summary. Don't count on the summary giving you all the information you need. It is full of information, but you're missing a lot there. As short a list of key terms as I think I've seen in any chapter, so that's not going to give you everything you need. You're applying the concepts, 45 questions, maybe a slight bit short of normal, but not much. That's fairly close to normal. Questions for thought, 18's about normal. For further analysis, maybe a little less so. And then you have the parallel exercises that you can do if you'd like. Next time, we skip 21, which is geologic time. We skip 22, which is atmosphere of the Earth. I wish we had time for that. That's pretty interesting. We're going to hit some of it in chapter 23. We just didn't have time to do both. So we'll pick up next time in chapter 23, weather and climate. Okay, let me end the slideshow. And I'm going to pause. Well, let's see. Maybe not quite yet. My thing out. Sometimes I forget to take these out, so while I think about it, I'll take that out. Okay. While I've still got the system on, let me pass out your lab to you. Kayla, if you want to turn on the light, you can. Thank you. Add a little light to the subject. Add a little light on the subject, something like that. Okay. And again, let me encourage you, get your labs and tests caught up and in. Now, is anyone here who did not get the Chapter 19 take-home test?
And the lab.
And the lab. Okay. And then the last lab was latitude and longitude. And you can hear most of it over YouTube. You need one too? Okay. But you got the technical data. All right. Seems like there's still somebody who hasn't gotten the lab, so I have one more copy here. Okay. Huh? I'm going to pass that out right now. Okay. But I mean, the last lab, I have one copy left. So somebody didn't get it. All right, here's today's lab.
Hey, did you get the last lab from 18 back yet?
Didn't I just give it to you, latitude and longitude?
This 19. About somebody the last lab 18.
Okay.
Did we get it back?
Oh, did you get it back?
Yeah.
No, not everybody's turned it in yet. I'm sorry. I thought you were asking if I had a copy of it. I'm going to turn this off for right now. I may turn it back on later. Okay, here's today's lab. Okay? Oh, sorry. Okay. One, test, three. Okay. We're only missing two, so we're about right. Okay. Let's talk about what today's lab's going to be. For those who were here last time, you will probably recognize this. This is the map of Alabama, which we used last time for latitude and longitude of cities in Alabama or towns in Alabama. We're going to use it today for a different reason. But if you read the first part, experiment 45, there's several different types of maps. One of the maps that we had back there that we used for the U.S. was a road map. And the main features on that are highways. Okay? It did have latitude and longitude, that's why we used it last time. And it showed things like rivers and lakes and things like that, and city limits and things like that, but it was mostly a road map. This, however, may have some roads on it. It does, but not all of them. But this is mostly featuring topographic maps, and that's why it's called topo maps, topographic maps of the entire state. Okay? Now, there are others that show geologic maps, which show rock features and things like that. We're going to focus on the topographic maps. Now, I know you won't be able to see this from my handling it here, but actually this cover isn't bad because it's probably blown up as much as anything. This is up around Albertville and Boaz and Gunnersville in the northeastern part of the state. There's Scottsboro up there. Now, you see roads are on here. Sure, they're listed. Cities are on here. They're listed. Some city streets and things. But the main features of this, if you'll see here, you see these little sort of grayish lines in between other areas. And they sort of sometimes will enclose an area. What these are topographic lines. Okay? Now, let me reference this to something that you might be a little more familiar with. Have you ever watched the weather maps on television and how they have sort of, they won't be circles, but they'll be shapes that go around and you'll have L's or H's, low pressure areas, high pressure areas. Well, those lines around those are called isobars. Iso means same, bars mean barometric pressure. That's where the barometric pressure is the same. So around the low pressure area, the ones closest to it might be down around 30 inches, and then 30.5 and 31 and 32. Yeah, it's getting higher as you go up. The high pressure areas may have 32, and then as you go out, 31, 30. Yeah, and so they're isobars, areas of equal barometric pressure around high pressure or low pressure. What these are isoclines. These are lines that show areas of equal elevation. Okay? Now, obviously on this floor, everything here is at one elevation. Okay? If you went out to the hillside there, here you're at one elevation there, you go down there, you're at another elevation, go down another. So if you drew that, you would have lines that parallel the drop-off. Okay? Those are isobars. That's what we're looking at in topographic maps. Okay? Not the roads, not the rivers and things like this, but usually, and sometimes they're related to the lake, like Gunnersville Lake, you'll see isoclines here parallel kind of with each other as you go up in elevation from the lakeside. And you can pick those out here. Okay? You'll see a creek here, and the lines will bend and go along the creek because the creek's basically a water level. Okay? So those are your isoclines. And that's what topographic maps show you. Okay? Now, and here's a picture here. Notice a steep hillside there, and look at the isobars here. Really, 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 really close together because you're going up in elevation a very great amount in a very short distance. Okay? Whereas over here, where it's a lot more rounded, the isobars are isoclines are further apart. Now notice here, they have 100-foot contour, 200-foot contour, 260-foot contour. Contour means area of equal elevation. Whereas over here in the steep part, you'll have 275 is at the peak, 260, 200, but those are much closer together. Here it goes up as high, but they're much more spread out because it's not nearly as steep. That's what we're going to look at with topographic maps. So please read page 345, 346. You're going to find a lot of answers to your questions on those two pages. Now again, we're not got any soft play. We're not doing the materials part, and we're not doing the procedure part. But read up to that materials part. Okay? Don't read any of those procedures. But once you've read those two pages, 345 and 346, then you can answer the next 5 questions. Okay? Just like everything you need. Well, the 5th question is at the end. You answer whether you thought the lab was worthwhile or whatever. Then there's an invitation to inquiry. Now, this has a website in it. I'm not sure the website is still active.
It's not. I just tried it.
Okay. I figured it was because it hadn't been in the past, but sometimes they bring them back. So what you can do is Google or some other search engine and search for Devil's Tower National Monument, Wyoming. And put also in that search topographic map. Topographic map of Devil's Tower National Monument, Wyoming. Now, I only see a couple of computers in here. Do y'all think we need to run downstairs to the computer lab so all of you can get on the computer? Or as many of you want. It is a lab. You can get there together. Now, some of you may have phones. It's going to be harder to see on the telephone because it's such a small screen. So you want to go down there or not? You do. So let's head down that way, and we'll talk about the rest of it when we get there. I'll carry this, and carry your lab. Carry something to write with. I'll come back and get my stuff. So I need to carry my computer too. So hold on. It'll take me a little while. Go down to 256. You don't have to if you don't want to. Okay? We'll finish the lab down there, and you can leave from there if you'd like.
So is the only test I missed the take-home?
Second?
Is the only test last week the take-home?
Yeah, the take-home test. Yeah. Sorry about that. What's that? You don't have to. You can work here, but everybody else will be there. I'll be there to answer questions, so it's up to you. See, you're only one of 2 computers in the room. The rest of the people, if they don't need a computer, they gotta go get one. Yes. Have you finished the lab yet? we'll work on the lab, and when you finish the lab, then I can do the test. Now, also, goodness, I'm going blank on your name. Jessica, I'm going to be carrying this downstairs too, and this is a big part of the lab, this book here. So, yeah. Okay, thank you. Finished already? Oh, okay. Okay, so let's head down that way. Let me put this on pause for now. Okay. Wrong side. Okay. All right. So, if you can get on your computers, let me see. Let me turn on my. Sorry, I'm going to have to stay sort of close here because, well, I thought I turned that off and it didn't go off. So I recorded all that. Sorry about that. I reached down and intentionally tried to turn it off, and I still was recording. So, had a lot of dead time, folks. Okay, so your lab today, the first 5 questions are on page 347 and 348, based on the reading on page 345 and 346. So, read those, answer those, especially the 4 questions, and then question 5 at the end, you can answer that. The next 5 points are on page 349, and that's where you need your computers. And what you need to do is go into some search, Google or whatever you want to use. I'm sorry, I keep forgetting I need to be talking to the computer. Go to Google or whatever you're going to use and go for topographic map, Devil's Tower National Monument, Wyoming. And find the relief map, they call it that too, topographic map of Devil's Tower. Then you answer these 5 questions. Now, I want you to just notice, what's the difference between, this is on page 349, sorry. What's the difference in question 1 and question 3? on page 349. What do you think the difference is? Question 1, what is the elevation of Devil's Tower? Question 3, what is the approximate height of Devil's Tower? What's the difference between those two?
Is elevation sea level?
So elevation is measured above sea level, okay? And I guarantee you Devil's Tower in Wyoming is somewhere way far from the sea. So you're already at a pretty high elevation. That's going to be the number you read somewhere there. What's the height then? Yeah, the difference between the base and the top. So you'll have to do a subtraction there to get your height. Now, I don't know, depending on what map you look at, that may be in feet, it may be in meters. You have to put the units down that correspond. Okay, so that's only 10 questions worth. What are you going to do for the next 15 points on your lab? Actually, it's going to turn out being closer to 16. That's where this book comes in. The Alabama Atlas and Gazetteer topographic maps of the entire state. Okay? I was referring to these before. Now, if you want to know where you are on this, if you look at the back cover, you'll see that these approximate rectangles here go from 16 in the far northwest corner of the state, across to 21, then 22 to 27, and on down till you get 62 and 63 at the bottom. So that's going to give you the numbers that you're referring to here. So for instance, I just happened to open to Scottsboro, okay, same one that was on the cover. Chattanooga is shown up here. This is page 20 and 21, and if you go back here, there's 20, and there's 21, and there's Chattanooga right there. Well, you don't quite see it here, but that's where you are. So the page numbers in the text here correspond to the numbers on the back of the thing. So if you want to get somewhere near where you live, my guess you live near 30 and 31, okay? If you want to go somewhere else, well, what you need to do is go different parts of the state, okay? So, here's what I want you to put down. You got to do 15 points worth here, and the first thing you put down, choose a page number, okay? All right, let me get my pen out. So, let me get my pen set up. Page numbers, and it's actually going to be 2 page numbers, 30, 31, 24, 25, something like that. So that would be 2 page numbers, okay? Then what I want you to do is find a feature on those pages, okay? Find a feature where you see those topographic lines being very close together, okay? Name a feature on that. And I happen to turn to a page, very obvious, several things on here, okay? Where the lines are close together, okay? So the second thing is features or location where topographic lines are close. Okay? And then, what does that mean? And when you're reading in your part, you've already answered that question. Then, find a place where the topographic lines are far apart. And then what does that mean? Okay? All right? So there's 1, 2, 3, 4, 5. Okay? Do 3 different page numbers. Okay? Sets of page numbers. Pairs of pages. Find a place on each place where the lines are close together, where they're far apart, the meaning of being close together and the meaning of being far apart. Does that make sense? That gives you 1, 2, 3, 4, 5. Yeah. 3 times 5 is 15. There's your additional 15 points. Okay? Does that make sense? If you want to do another pair of page numbers or so, you can. You can work together. You can work individually. Some of you can be working on the first 5 questions. Some of you can be working on the Devil's Tower. And some of you can be working on this. Okay?
So there are 4 questions. We answer them.
Yeah. Okay.
Different page numbers.
Page numbers. You just pick your page numbers. Now, if I were you, I would avoid some of these down here in the coastal plain. You're not going to find many lines close together. So pick things that are up in here, basically. You'll have 2 page numbers, 30, 31, 24, 25, something like that, okay? And on that page, on that spread, like this one is 18 and 19, okay? That would be 18 and 19. Then find some feature, something where the lines are close together that's labeled on here, and then put that name in. Tell what that means. Then find some place on those 2 pages where these total lines are far apart, long way between them. Find the feature there, a town, or anything that you might find where they're far apart, and then what's the meaning of that? Then go to another set of pages and another set of pages, and find all of those in that. So anyone who wants to, y'all can share, you can work together, you can work separately. But that's allowed today. Make sense? You want me to leave this up? And by the way, your page here under Invitation to Inquiry, you can work this on that, or you got the whole back page there. In fact, I would say Invitation to Inquiry, do that on page 349. On the back side of that, do this right here. Maybe like that. However you want to do it. Yes?
The third word all in the middle, what that mean?
Say that again?
The third word that's in the middle, what that mean?
This one?
Yeah.
Meaning, I'm sorry, my writing stinks. And that one too. What does this mean for the lines to be close together? What does this mean for the lines to be, far apart? Okay? You can make yours look a lot nicer than mine. Okay? Okay? Any questions? Okay, I'm going to go back and forth, bringing the rest of my stuff down here. You want me to leave this up here? Well, in case anyone else comes in. See, I don't know how some people turn in the lab already when they hadn't even heard what they had to do. But that's up to them. Okay, I'm going to put this. Okay. For instance, the team that's on it now are on pages 48 and 49. Okay? Now, what they're going to look for are places, some feature on that where the topographic lines are very close together. If you have trouble finding those, ask me. I'll have to show you which ones are the topographic lines. Find some feature where they're close together, fill that in from that page. Then, this says the meaning. What does it mean for those lines to be close together? That was one of the questions you answered on the first 5 questions, right? Okay? Then find a place on that same 2 pages where they're far apart, where there's a long distance between the topographic map. Find some feature that labels a place like that. Fill that in here. And then what does that mean? And that probably also, if it wasn't in the question, it's pretty close to it.
You have to do that
For 3 different page numbers. Pairs of page number. 48, 49, 16, 17, 30, 31, whatever. Any pages numbers you choose out of there. You can go with them. You can do it with them if you want to. Or you can wait to refer. That's why I was encouraging everybody to get down here, so some people could be doing the first group, some could be doing the second group, some could be doing the third group, and then you can rotate it around.
very close and there's a lot of elevations, but it doesn't tend to just swoop up like natural landscape. That's the wild thing about it. Like, we couldn't find like mountain ranges that were really full.
Where are you looking to? Oh, that's a line. Near Grove Hill. You see line close together? Okay, that's what it was.
Close enough for you?
Okay, well, the property would be fine. If they're close together, that's the property.
But we're seeking explanation, because there's no,
Okay, that means it's, what does it mean for lines to be close together?
Just walkways and
Fairly
mountainous place.
So it's not mountainous, they're not that close together, but it would be steep. And places where they're far apart, that would be flat. Exactly. So those are going to be the same no matter what, almost.
All right, just making sure. And we just have to do three of those, so that equals
Yeah.
15 questions.
Pairs of pages.
So we'll have a test next week.
Pardon?
We have a test on Thursday.
Yeah, you have a test on the chapter you just finished today, on Thursday, the last 30 minutes. And then before that, we will be doing chapter 23. And,
I'll turn in my chapter 19 test.
okay, all right, there we go.
Thank you.
Okay, are there any more questions that I could answer? Otherwise, I can turn off the thing and have it start loading. What you think? Y'all got the format you need? Okay, I'm going to turn it off.